All right, the next section is 16.1 vector fields. What is a vector field? A vector field is effectively a function that spits out a vector. So, in that sense, and using that definition, then we've already been working with vector fields. We just haven't been calling them that, which is perfectly fine. So, what we can do now is actually take a look at what a vector field looks like. So a vector field, what we can go ahead and do here, we can add a vector field object, so a vector field, go ahead and do that. We can also restrict the view to 2D if we want to. You can have a vector field in any dimension, but let's go ahead and start with 2D to keep it simple. And also let's make it a little bit simpler in that we're going to go ahead and make these not variables but constants. So if we do that, we're going to go ahead and see a vector field. So what it's doing is at every single point, it's placing this vector 1 unit to the right and 1 unit upward in the y direction. The z component is 0 because we're just pretending like it's a two-dimensional vector field. So this is what we have, and if you pay attention, you'll notice that the distance, the scale for x and y, they're equal, and 1 unit is this. So technically this vector should actually point, beginning here, point all the way up to here. Why is it only, not that full distance? Well, a lot of times when you're visualizing a vector field, it can get pretty crazy, the length of the arrows. So there's a lot of software that produces vector fields has an option over here for you to scale the vector's length by a certain number. So in this way, since we're dividing all the vectors by 4, all these vectors have 1/4 the length that they otherwise would have. So if we just put 1 in here, this means we're going to preserve the vector's length and keep it the same as it actually, as the vector field's definition over here says it should be. So really this vector should have a length of square root of 2. So if we go ahead and do that, you'll see that the vectors, they each are pointing, this vector that starts here does terminate over here, but you can see it's very tricky to read this. So a lot of times for legibility, at least to get a sense of the vector field's direction, we'll use this little feature. And of course, we can also say how many vectors we'd like along each axis. We can put as many as we'd like. Let's take it back to the default here. But that's what a vector field is. At every single location, we're gonna place this vector 1, 1. Again, I'm pretending this is two-dimensional, so I'm completely ignoring this z component of the vector field, p. Let's take a look at one that's a little bit more interesting in that we're going to put a variable here. So let's say we keep y, y1, but we'll make x, the x component of the vector field, equal to x. Okay, so what exactly is happening here? Well, what this is doing is at the point 0, 0, let's start the origin. So at the point 0, 0, it's going to place the vector, well, at the origin, x is equal to 0. So it places the vector 0, 1, 0. So that's going to point upward in the y direction 1 unit. In fact, any vector with x coordinate 0, so anything on the y-axis itself, its x component of the vector field will just be 0. So it will simply graph a vector pointing upward. Now if I move to the right, let's say over here at x equals 1, so the point on the x-axis 1, 0, well now this component right here, m, the x component of the vector field, at the point x equals 1, at the point 1, 0, the x value is 1, so it points the vector 1, 1, which is this vector. Appropriately scaled, of course, since we still have this option enabled. And as you can see, as you move to the right, in other words, as x gets bigger, the vector points more in the x direction. So it's longer. It's getting longer as you move to the right. Always the same change in y, so the rise is always the same for each vector, no matter how far to the right or how far to the left you look. Always the same change in y, but your change in x, your run, so to speak, is getting bigger. And we could even make it more complicated where we could maybe put an x in both locations. So now, as you move to the right, since the change in x and the change in y are going to be the same amount, that's why all these vectors have an angle of 45 degrees with the horizontal. So at this point here, let's go to this point up here. -2, 1, right here. At this point, the vector should point to the left 2 and down 2. Why down 2? Well, because the y component of the vector field is also the x value or x coordinate of the point. Okay. All right, so if we take off this, we toggle this choice on or off, we can look at a new vector field. So here's a vector field. It's in 3 dimensions. Now for this vector field, I've given it the z component 0. So this vector field effectively looks the same no matter what your z value is. But we could change this and maybe make it something else. Maybe let's also make this x. So now our vector field, see, it's sort of tilting up a little bit. And we can let's do some samples in the z direction. Oh, we've got something quite complicated now. Let's maybe dial that back a bit. And this is what the vector field looks like. We can also maybe make it x times y times z. Something very wild. Something very wild indeed. So really what a vector field is doing is you plug in a point, x, y, z, into this vector field, and it's going to spit out a vector. And then at that point, x, y, z, you graph the vector that's given by the vector field. That's all a vector field is. We'll come back to the visualization of vector fields later, but that's the basic idea, and this is how you would use it in CalcPlot. Okay. Returning to our notes, we'll get started here and taking a look at just highlighting a few pieces of information. Remark number 1 is important in sketching and drawing a vector field. When drawing a vector field f, the vector f at some point p is drawn based at the point p. We already have practice doing this with, for instance, using the derivative r prime of t of a vector parameterization of a path. When you when you draw the tangent vector, you draw it at the point on the curve. So this is that same idea. So let's take a look at this example here. What vector corresponds to the point P equals 2, 4, 2 if the vector field is f is equal to y minus z x z minus square root of y? Well, to figure this out, all you would do is take your vector field f, and you'd plug in your point P. So this is y minus z, so 4 minus 2, comma x, which is 2, comma 2 minus the square root of y, which is square root of 4. And then we simplify, so 2, 2 minus 2, 0. So this is the vector that we would sketch at the point 2, 4, 2. Some other little things down here. Definition 2, a unit vector field is simply a vector field where the length of the vector field at every single point is length 1. we already know how to make a vector into a unit vector, right? So for instance here, if we had the vector, let's say u, which is equal to 1, 2, 4, then to make u into a unit vector, we would simply divide u by its own length. So we'd have the vector 1, 2, 4 divided by whatever the square root of 1 plus 4 plus 16 is. So 1, 2, 4 divided by the square root of 21. Well, we can do the same thing making a unit vector field. For instance, if we start with a vector field, capital F is x, y squared, I'll do a two-dimensional vector field, then we can make this into a unit vector field by taking the vector and dividing by its own length. So we'd have x comma y squared divided by the square root of x squared plus y to the fourth. And that would be a unit vector field. So no different, because ultimately a vector field is just a vector. It's a variable vector, but it's a vector. Okay, radial vector field, this is not terribly important for our class. It has more physical applications, but you're not going to be specifically asked to recognize what a radial vector field is, so we'll just go on and move past that. Some examples here of radial unit vectors, and moving on to the divergence operator.